Liquefied natural gas (LNG) is natural gas that has been cooled to a liquid state at about -260 degrees Fahrenheit for shipping and storage. The volume of natural gas in its liquid state is about 600 times smaller than its volume in its gaseous state. Essentially, the LNG value chain can be divided into four main steps, and they are: 1. Natural gas production and exploration. 2. Liquefaction and storage. 3. Shipping. 4. Receiving, regasification, and distribution. Production and exploration include extracting raw natural gas from reservoirs, rough on-site processing, and bringing the gas from the site of extraction to a treatment facility or LNG plant. When brought to an LNG plant, the gas is processed and treated through the gas liquefaction cycle before getting stored and prepared for transport. Liquefying natural gas is a way to move natural gas long distances when pipeline transport is not feasible. Markets that are too far away from producing regions to be connected directly to pipelines have access to natural gas because of LNG. In its compact liquid form, natural gas can be shipped in special tankers to terminals around the world. At these terminals, the LNG is returned to its gaseous state and transported by pipelines to distribution companies, industrial consumers, and power plants. For large volume ocean transports, LNG is loaded onto double-hulled ships, which are used for both safety and insulating purposes. Once it arrives at the receiving port, LNG is offloaded into insulated storage tanks and regasified for entrance into a pipeline distribution network. Liquefied natural gas terminals. An LNG terminal is a facility that handles the import and export of LNG. It comprises equipment for loading and unloading of LNG to and from ocean-going tankers, for transfer across the site, for liquefaction, regasification, processing, storage, pumping, compression, and metering of LNG. Liquefied natural gas terminals can be classified as 1. Liquefaction terminals for the export of LNG, or 2. Regasification terminals for the import of LNG. LNG terminals may actually combine both functions. Regasification is the process of converting LNG from a liquid to a gaseous state. This requires significant quantities of heat energy to supply the enthalpy of vaporization of LNG and to heat it from -162 degrees Celsius to about 0 to 10 degrees Celsius for introduction into a pipeline. A series of heat exchangers are used to regasify the LNG. This may include submerged combustion vaporizers or an intermediate fluid exchanger, or the use of waste heat from a nearby plant, such as a power station. Final heating of the gas may use air or seawater heat exchangers. At times of low demand, gas may be withdrawn from a transmission system and liquefied and stored. There are several proprietary systems that are used to liquefy natural gas and turn it into LNG. Basic equipment in the LNG terminal. The LNG storage tank. An LNG storage tank is a specialized type of storage tank used for the storage of liquefied natural gas. LNG storage tanks can be found in ground, above the ground, or in LNG carriers. An LNG tank is built to have an inner compartment of cryogenic steel with 9% of nickel content, surrounded by an outer tank made up of a steel sheet and a pretensioned concrete wall for insulation. LNG is a cryogen and is kept in its liquid state at very low temperatures. The temperature within the tank will remain constant if the pressure is kept constant by allowing the boil-off gas to escape from the tank. This is known as auto-refrigeration. The most common type of tank is the full containment tank. Tanks vary greatly in size depending on usage. All piping connected to the LNG tanks, whether above the ground or in ground, are routed through the top of the vessel. This mitigates against the loss of containment in the event of a piping breach. Floating storage and regasification unit. A floating storage and regasification unit is an LNG terminal whose main structure is a special ship moored near a port. Unloading and loading of LNG. Terminal facilities include jetties and piers with articulated loading and unloading arms for transferring LNG between ship and shore. It also includes the piping used to transport LNG between the loading arms and the storage and processing facilities at the terminal. The loading and unloading arms and pipeworks are insulated to prevent heat gain from the air to minimize the vaporization of LNG. Tankers being loaded with LNG displace the vapor volume in their tanks. This gas is routed to boiler for gas recovery storage tanks. Gas may then be compressed and fed into the local gas network, or it may be routed to the liquefaction plant and returned as liquid to the LNG storage tanks. LNG pumps and compressors. After natural gas has been processed to remove impurities to meet quality standards, it is sent to high-capacity compressors to be compressed and fed into a liquefaction line to produce LNG. Most LNG plants using cryogenic systems install turbo expanders, where a sudden decrease in pressure cools the gas and uses the energy from the expansion in the compressors of the same process. Pumps play a range of critical roles throughout the process of converting gas into LNG, storing it, and loading and unloading LNG tankers. Pumps that handle LNG are very reliable. They are specialized for operation under cryogenic conditions and submersion of the pump units. The pumps that transport LNG, such as those that move it into, around and out of the storage tanks on LNG tankers, must operate at cryogenic temperatures. The pumps used must be highly reliable, durable, and constructed of compatible materials. For LNG applications, submerged motor-driven cryogenic pumps are used. Some of the benefits of submerged operation include that, as a cryogenic fluid, LNG is an excellent electrical insulator, and the motor is completely isolated from oxygen in the atmosphere, eliminating the risks of fire or explosion. This design also removes the need for rotating seals, which can be problematic and introduce a potential point of failure. Submerged LNG pumps are constructed as a single unit, with the pump mounted on the same shaft as the motor to be submerged in the LNG. Liquefied natural gas metering. The principle of operation for the LNG flow systems is using the turbine flow meter specifically to obtain an accurate volumetric flow rate of the LNG being delivered. Secondly, the use of the ROTD sensor to accurately measure the temperature of the LNG being delivered. Thirdly, the pressure sensor to determine the pressure of the LNG being delivered. After that, all three signals are transmitted to the ICE cryogenic flow computer. At that point, the computer integrates the flow rate signal over time to determine the total volume of LNG delivered. The flow computer uses the temperature and pressure signals to determine the density of the LNG in real time against preloaded LNG fluid property tables. Finally, by knowing the volumetric total flow and the density of the LNG, the total mass or compensated volume of the LNG delivered can be determined within the legal requirements. LNG terminal control systems. There are individual digital control systems for each piece of equipment, registering variables and sending signals to actuators that will move valves, activate pumps, or perform other functions. There is a tendency to integrate all installations under one computerized system, which increases the quality and safety of technological processes. There are also sophisticated systems such as the advanced management processes that integrate existing digital control systems and provide a clear structuring of the management process. Advanced management processes use multi-parameter mechanisms that are described by a process and optimize each operation by making changes to several execution algorithms. LNG plants make use of SCADA, that is, Supervised Control and Data Acquisition Systems, which monitor the operation of wells. These systems can be connected to a variety of sensors, including indirect composition sensors that use valves as a final control element. Typically, such a system has a series of distributed pressure, temperature, and flow sensors combined with a reliable instrument that allows composition analysis and gas component determinations. These are tied to the central operating system, which sends signals to the actuators. LNG terminal safety measures. LNG plant safety systems integrate those plants, devices, equipment, and processes that are aimed at improving the lives of people in nearby communities and workers, as well as ensuring the integrity of equipment, minimizing the costs associated with failures, accidents, and any hazardous situation. Liquefied natural gas plants must include emergency shutdown and valve closure systems to avoid gas leaks in process equipment, ventilation and vapor recovery systems. Boilers or combustion systems must be designed to burn at least 80% of the gas being handled, as this is the last option in the event of a plant emergency. Safety devices include sealing valves, anti-static systems, and electrical equipment protection, bursting discs, fire traps, fire protecting systems, flood protection systems, seismic resistant equipment. All equipment in an LNG plant must be designed for the extremely high pressure and temperature conditions it maintains, in addition to the safety margins for filling and storing gas. All measures that are taken into account by engineering teams when designing safety systems must be designed for complete equipment failure. Also, engineers consider existing relationships with other equipment by developing failure safety matrices and procedures that allow operators to act in the right way to resolve the problem.